Hello everyone, welcome back to FE Review Session, Mechanical Portion. This is Nicholas, and I hope we can have some fun solving some problems today. We are going to be looking at the first law of thermodynamics specific problems. I'm going to go through about 6 of them, number 1 through 6, and we're going to have some fun. Alright, let us start with problem number 1. We have the forebay of a dam feeds 900 megagrams per second of water to an electrical engineering plant. So we have a dam that feeds about 900 megagrams per second of water to an electrical engineering plant. The water is a specific volume of 0.001 meters cubed per kilogram. All right. It enters the generator at 900 kilopascals. Is our initial pressure, excuse me. Okay. I'm not sure why it doesn't want me to write legibly here. Okay. We're gonna call it our P1. So, and we'll have our P2 200 kilopascals. Kinetic and potential energy changes are insignificant. What is most nearly the power generated by the dam? All right. So we want to find out what is the power generated, and we have two pressures, a specific volume and a mass flow rate. Immediately, what you can think of is we are in a forebay of a dam, and we're being fed into an electrical engineering plant, and we're entering a generator. So we're going to need to know what are the components of this generator. We know there's going to have to be a turbine in there. That's what's going to generate the power. So we're going to have a work of a turbine and a pump in order to compress the water, or yes, water. So the work of a pump. Now you may remember what these are, the specific equations, but if you want what they are generally, it's going to be our enthalpy of the initial point minus the enthalpy of the exit point, or initial minus final. Call it E. And the next one why is my pen being so weird over here? Interesting. Work of the pump is going to be the same as the above. Hold on, this is not working out all right. Let's see. Why is this? Huh. Okay, that's better. Okay, so oh, you are just not having me today. Okay, Well, it's okay. That's exit enthalpy. Now, you may remember at the work of a pump, you may be able to simplify that if your medium is incompressible. If that's the case, then you can simplify this to VI times the change in pressure, V delta P. And the turbine work will have to remain the same. So, we can assume for this specific problem that it's adiabatic. So the changes in velocity and elevation will be insignificant. We can also assume that all of the steady flow energy equations, all of the terms in the steady flow will drop out except for enthalpy and work. So, hence why we have the equations above. So now we just need to figure out, okay, what is the work of the pump? We can get that. No, we don't actually need that. Here we can get the total work done by the system mv delta t, m dot v delta p. We can figure out the total work generated by using this relation right here. Even though these are true, we don't necessarily need to use the individual equipment unless it was specifically asking for the specific work of the pump or the turbine. So with this, we can plug in our numbers. We have 900 megagrams per second. We're going to have to convert this, multiply by 0.001. That's going to be meters cubed per kilogram. No, meters cubed. No, this is our. That's our specific volume. We'll have to convert this to kilograms to get this to work. And then we're going to multiply by our 900 kilopascals minus 200 kilopascals. And altogether, what we should get as a result is going to be 630 megawatts. This corresponds to answer letter B. The problems in this section are a bit on the longer side. Oh my phone will die before I'm done with this. Let's hope not. All right. Let's quickly then move on to problem number 2. Problem number 2 is a conceptual problem. It asks which of the following principles is the closest interpretation of the first law of thermodynamics for a closed system. We have A. The mass within a control volume does not change. Mass, no change. In control, that one spot is just not good. In a control volume, We have B, which is the net energy crossing the system boundary equals the change in the inside system. Equals okay, C, which is the change of total energy, so delta total E equal to rate of work and then D, all real processes. So I apologize for my handwriting. I'm trying to make this thing work. Tend toward increased disorder. Okay, with these four, which one of these is most closely is the closest interpretation of the first law of thermodynamics for closed systems? Now, first and foremost, we know that. Let us first define what is the first law of thermodynamics. First law of thermodynamics is the change or the heat added across the system boundary minus the work going out of the system boundary is equal to the change in internal, really. It's equal to the change in internal energy. That's supposed to be a U, but it doesn't want me to draw a U, so I'm going to put down here. Delta U, dang. With that being said, we can eliminate D right off the bat. Because that talks about creating disorder, which is related to entropy, which is not what we're dealing with for this law. We have total energy is equal to the rate of work. Rate of work would be considered power. So we're not dealing with power either, so that one can be crossed out. Change in the system boundary equal to the energy change inside. That could be right. We'll keep that one for now in A. This one's hard to read. Gosh darn it. The mass within a closed control volume does not change. Okay, control volume and whatnot is also not what we are talking about. So that leaves with just one answer choice, and that is B. Which is actually, it's pretty telegraphed by this equation, actually. The change in incoming heat minus the work going out is equal to the change in internal energy. It's kind of simulating the conservation of energy, which is pretty much what the first law is. All right, cool. All right, let's move on. Problem number 3. Actually directly related to the previous, what is the origin of the energy conservation equation used in flow systems? We got Newton's first law. We have Newton's second law. Oh boy. All right. First law of thermodynamics. I believe you guys already know the answer to this. And second law of thermodynamics. Judging by how we answered the previous question, the answer to this one is pretty telegraphed as well, since we know that we have two different energy balances for the first law of thermodynamics. I think we can make a safe guess that this is probably going to be the answer. Let's check the other ones first. Newton's first law. Newton's first law states that an object in motion tends to stay in motion. You could potentially relate that to energy conservation, but not for the equation that's specifically used for flow systems, so that one's out. B, second law of motion. Force is equal to mass times acceleration. Again, you could use this to find some conservation equations, but not the specific one we want, so we can cross that out too. Second law of thermodynamics, I don't believe that applies here either. So our only choice that we can go with here is the first law of thermodynamics. And that's what we go with. That is the answer. C. Oh boy. All right, let's move into problem number 4. Problem number 4. Steam flows into a turbine at a rate of 10 kilograms per second. Flow in steam. And then 10 kilowatts of heat are lost from the turbine. All right, elevation, kinetic energy are negligible. What is the power output? Okay, we have in conditions. Pressure, temperature, quality. 1 MPa, 350 degrees C, unknown, 100%. 1 MPa, not known. Okay. What is, oh, sorry, this is out. Okay. We want to find the power output. Okay. Okay, we can use the steam tables with this given information for in-out conditions along with with our in and out conditions, and we can get what the enthalpy in and the enthalpy out are. This is going to be 3157.7 kilojoules per kilogram, and this is going to be 2675.5 kilojoules per kilogram. Well, and with that, we can go ahead and calculate our power, which is going to be, again, the equation we saw earlier, only a little different. We're going to have m dot times the change in enthalpy, Hi minus He, plus the added heat, or subtract the added heat. Since we are losing 10 kilowatts, that is going to be our Q. Okay, I would write it here, but it doesn't want me to. After calculating through this, what do we get? I'm running low on time, so I will write out to the algebra for you. We have m dot is up at the top, which is 10, and plus we're going to actually subtract this 10 kilowatts from the total final answer. So we're going to have our answer be 4,812 kilowatts, which is most closely representative of 4,800 kilowatts, which is answer choice C. Again, a lot of C's this time. Sweetness. All right, we will move on to problem number 5 now. Which type of process is the equation and dq is equal to T ds valid? All right. What type of process is this? Irreversible, isothermal, reversible, or isobaric? dq equals to T ds. What is S? If we remember, S is entropy. So the change in Q, dq, the rate of change of Q, equals to temperature times change of entropy. We have to look at this equal sign between them. We have a change in something, change in heat, Q, change in heat, rate of heat transfer is equal to a change in entropy times our temperature. Because of the equal sign, we know that this can't be something that's irreversible. It must be a reversible process because of the equal sign separating them. And in that case, since we know this is already the answer that you should go for. If we know that it has to be a reversible process because of the equal sign, then we can go with C already. And just to clarify, if this were not reversible, there would have to be a less than or greater than sign between the two to know that it's not fully reversible. There is a portion of one that will be greater than the other, or vice versa. So this one we can show our answer to be C again. All right. Now up next we have a very long problem number 6. Hopefully you enjoyed this one. Steam is quickly compressed by a piston in a cylinder with a compression ratio, I guess I'll call it CR, is 4:1. And the steam is at atmospheric pressure. P1 is 1 atm, I guess. Let's go with that. Before compression, the temperature T1 is going to be 400 Kelvin. And is also at atmospheric pressure and 400 degrees Kelvin. After compression, temperature is 600 Kelvin. What is most nearly the work per unit mass done by the piston specifically? Okay, so let's figure out what we need to find. We want the work done by this piston. So let's do some energy balance. We know that the work out is going to be, we're going to use the first law of thermodynamics here. Total heat subtracted by the internal energy is equal, well, we know that this is going to be 0 because we're going to assume this is an adiabatic process because there's a low heat loss. So we know we're just going to have U2 minus U1, or U1 minus U2 if we distribute that negative sign. So we have work out, or I should say negative work out, equal to our work in first law of thermodynamics, which is equal to U2 minus U1. I decided to move the negative sign back to the W out so we could write this relation. So all we need to do basically is find U2 and U1. How do we do that? So we have some information that we were given. We know that the steam was initially at 400 degrees Kelvin. Let us convert this to Celsius. Please let me write here. 127. Which, now we have to look at our steam tables. For 127 degrees C at 1 atm. We've got to find out our position. Where are we? If you want to take a look at them, you may. 1 atm is 0.01. Sorry, not 0.0. 0.10135 MPa. So if you look at the steam tables, you'll see that we're in superheated vapor section. You can find that by looking at 127 degrees Celsius and looking at the corresponding pressure, seeing that we're either above the pressure line, or looking at the pressure and seeing that we're above the temperature line. You can look at either one of them. Okay. With the pieces of information that we have, the temperature and the pressure, we can calculate the internal energy and specific volume from the superheated table. We can use the superheated table at 0.10 MPa, and we could interpolate with our temperature at 127 degrees C. With that, we can get our specific volume to be 1.826 meters cubed per kilogram, and our U1, which is 2548 kilojoules per kilogram. Now you may wonder, why did we calculate this term? Well, if you may remember, at the beginning of this, we were given a compression ratio. We were given a ratio for the two volumes, 4:1. So we can use that, actually. We're going to need this to be able to find our specific volume for the second U, I guess the out section, and we can use that to go back into the tables to find our U2. So we have this, we'll keep this. We will go back to red. We can calculate our specific volume for two by using V1 divided by our CR, which is 1.8. Nope, you can't. I'm going to write down here 1.826 over 4, which is going to be 0.456 meters cubed per kilogram. With that ratio, allows us to get, that's a 456. We were able to get another piece of information so we can triangulate our position for the final pressure, final temperature, the end point for our situation. We calculated for the initial point, that's what we got, U1. But now we need to get our out energy, so we can get the difference of that and get the total energy change, which is going to be our work. So now we're going to look at the 600 Kelvin point. Convert that. That's going to be 327 degrees C. And then we have our volume as well. So we can use our superheated table. We also know this is in the superheated section. We can look at our 0.60 MPa section and 327 degrees C. With this, in case you're wondering, we use the specific volume in this table along with the temperature to find out what the to figure out this. This is an unknown. We use the temperature and the specific volume to figure out, to triangulate this particular quantity. And after we do get it, we figure out, cool, this is where it is. Let's look and see what our U2 is. And then you can find the U2 to be about 2844 kilojoules per kilogram. So now we know U2 minus U1 is going to be our work, which will give us a value of about 296 kilojoules per kilogram. This most closely corresponds to the 300 kilojoules per kilogram offered in answer choice A. And that is that problem for you guys. Seems I am out of time. Hopefully you enjoyed these 6 problems we went over. If you have any questions, please leave a comment in the section below. If you think the video was great, also you can tell us there, leave a like as well. If you think we need to improve on something, please let us know. We are always open for improvement and constructive feedback. All right. Well, I guess then, without further ado, I'll let you all get on with your busy day. And I will see you again next week. Take care, everyone.